All right. Even my kids can see it. All right, great. So thank you for inviting me. I'm going to talk about black holes, and I want to settle the issue once and for all. Okay? Black holes are real. واللي مش معاجبه خليني ابقى اشوف بعد الحظر يعني. All right. So first things first. What is a black hole? A black hole is basically a hole and it's black. Okay, so what? So I haven't explained anything. How can we describe what a black hole is? I don't like the massive something is so massive that it becomes a black hole, because that doesn't really explain completely what a black hole is. Okay, because there are black holes that are very small or black holes that are very large. So this mass thing is not the real issue here. So how can we define it? We can define it in the following way. We can say that it is an object whose gravity is so strong that not even light can escape from its surface. Okay? It's an object. That's for now. Just say it's an object. Later on, I will define what that object is. Okay? For now, I'm going to say it's an object whose gravity is so strong that not even light can escape from its surface. It's literally a hole in space-time. Okay? Why I'm saying space-time? Because here we have to remember Uncle Al. Space, there's no such thing as space or time separate. They are a single entity called space-time. But okay, let's take it easy here and move step by step. All right. So what is that object? What do we really mean about it? Now, full disclosure here. If you don't like the equations, simply don't look at them. Okay? If you don't understand these equations, I'm not asking you to. You can still understand the talk, even if you do not understand the equations.
I closed my eyes, Dr. Sabra.
Okay, that's good. My argument is the following. That's my favorite argument. It has nothing to do with general relativity or anything. It has a formula here, especially this formula here. Later on the second page. Oops. Okay. Down. Okay. That if you put it in my exams, I'll give you a 0. But anyway. So you are all familiar with the escape velocity, or I'll make you familiar with the concept of escape velocity. If you have something, okay, and you want to shoot it up, the higher the speed, the higher the altitude it's going to reach, and then it falls down again, right? Okay? Now, turns out that from Earth's surface, the speed for that object to escape from Earth's gravity is 11 kilometers per second. Okay? And this escape speed, this escape velocity is related to the mass of the object and the radius from which you are shooting that object. Okay, so it depends on two things, the mass of the object and the radius from which you are shooting that object. Fine. So for Earth, shooting things from Earth's surface, if you shoot things vertically up at a speed of 11 kilometers per second, that thing can escape completely from Earth's gravity. Okay, that's one idea, put it aside. The second idea is, what's the fastest thing in the universe? Light, right? Light is the fastest thing in the universe. So a black hole is an object whose escape velocity from its surface is greater than the speed of light. So if you are standing on the surface of a black hole, and later on we'll see that there's no physical surface, ما في شيء قاسي, not as in this standing on a solid surface. It's a boundary in space around the center. We call it the event horizon. If you are standing on the event horizon and you hold and you have a flashlight, the photons from the flashlight will go up and then come back again. Go up and then come back again. Okay, so a black hole, now I give my full definition. A black hole is an object whose mass is contained within a region such that the escape velocity from the surface of that region is equal to the speed of light. Okay? The size of that region is characterized by the Schwarzschild radius, and it depends on the mass. So for every solar mass, it's 3 kilometers. So if somehow you manage to turn the sun into a black hole, شو بعرفني, Dr. Evil, whoever, your favorite villain, was able to turn the sun into a black hole, the radius of that black hole, the radius of its event horizon, the radius of that region within which you are going to pack all the mass of the sun will be 3 kilometers. From that radius, not even light can escape. 4 kilometers, you're free. You'll be tired. You'll climb out of the gravitational potential well of the black hole and you have lost a lot of energy, but still you can escape. If you are at the event horizon and shooting things upward, you cannot escape at all. Okay? The event horizon is, think of it as a one-way membrane. It's not a solid surface. It's just a boundary. Okay? It's, of course, everything is spherical, so it's a spherical surface. It's not a boundary, it's just a boundary. It's a mark on the map. Okay? So these are here, it's just basically takes the escape velocity and plots it as a function of radius for various sizes of black holes. All right, so let's see, you can see my cursor here. The red line is the speed of light. That's the limit. You cannot have velocities that are greater than the speed of light. So that's why we have this here red line. Okay, and this here shows you the escape velocities from various radii, and at the same time it allows us to calculate the radius of the black hole. Where is the radius of the black hole? It's the intersection between the escape velocity versus radius, these lines, the dotted, the dashed, and the dotted dashed, and the red line. So for example, the radius of a 3.3 million solar mass black hole is about 100 billion kilometers. And that's, by the way, the radius of the black hole in our galaxy. Okay, the bigger the black hole, of course, the bigger the radius of the Schwarzschild radius. The smallest is the one solar mass. It's around here. It doesn't even show on this plot. It's 3 kilometers. Remember, here it's this formula. Right? It's this one. The radius is given by this formula, and the run of escape velocity with radius and mass is given by this formula. Okay, if you're not good at math, don't worry. I'm not good at math either, so you're fine. Now, once you cross the event horizon, there's no way, there's no going back. Okay? Forget it. مش انه لا سوري نسيت شغله، نسيت المفاتيح بدي ارجع اجيبهم وارجع واجي. خلاص. You cannot, not even if you have a warp drive. You cannot. Once you cross the event horizon, you cannot go back. And the last picture of you to the whole universe will be just the moment before you cross the event horizon. So it'll be frozen. Your image will be frozen in time for eternity. So if you're just screaming, please help me, the last thing that people will see of you will be please help me, begging people to help you. So if you happen to fall into a black hole, please put on a brave face. You don't want to have your image frozen for eternity as a coward. Okay? ما تضحك العالم عليك. All right. Now, once you cross the event horizon, all roads will lead to the center. The center is called the singularity. Zero radius, infinite temperature, infinite density. The space between the event horizon and the density is empty. Nothing can hover there. So a black hole is very simple. It's just a singularity, and it's shrouded مغطاي بالevent horizon. Okay, and again, if the event horizon is not anything material, simply it's a mark on the map that nothing can cross that boundary. So technically, you say that all light cones, those who have taken special relativity know what I'm talking about. All light cones point inwards, and for very large, if it were here's the thing: the smaller the black hole, the stronger the tidal forces. The tidal forces is the differential force of gravity on your feet and on your head. So you get stretched and squeezed inside. That's called, you become like a spaghetti. Now, it turns out that the bigger the black hole, the weaker the tidal forces. So if you are falling onto a supermassive black hole, that like the black hole at the center of our galaxy, or the black hole in M87, I'll discuss that later towards the end, you will not feel any tidal forces. So you can cross the event horizon without feeling anything. But when will you learn that you have crossed the event horizon? When you can't retrace your steps. Now, what happens when you reach the singularity? No one knows. Now, little bit general relativity. General relativity says that mass curves space-time. So the mass of the black hole curves space-time so much. That's why we call it a hole. It curves space-time so much that it punctures, it drills a hole in space-time itself. Okay, and what is that hole? That hole is the singularity. It's not the event horizon. The event horizon covers the black hole. Okay? The event horizon covers the singularity. The hole in space-time is the singularity. The event horizon simply covers it. And that's the naked singularity conjecture, that nature does not like naked singularities. It always covers them up with event horizons. It's due to Hawking and Penrose in the 1970s. So what happens here's the, if you were, so this is, as I said, okay, the material is this purple thing. Okay, it looks purple on the screen. Yes, it's purple. And the event horizon is this. If there's material beyond the event horizon, then there's no black hole, and you have whatever star, planet, whatever you have. If somehow you were able to bring all that material and make it cross the event horizon, then the material will keep on collapsing and collapsing till you reach a singularity. So the black hole is very simple. It's maybe the simplest object there is. It's just a singularity with a region cordoned around it, مثل في محطوط طوق أمني حواليها، إنه إذا قطعته ما فيك ترجع. إذا قطعته من برا لجوا. إذا فتت عليه ما فيك ترجع. عادة نحن الطوق الأمني بيقول لك ممنوع تفوت على الطوق الأمني، هيدا عكس الطوق الأمني. أوكي؟ هيدا الإيفنت هورايزن هون is opposite to الطوق الأمني اللي نحن معودين عليه. If you cross it, you cannot leave. Now, what is the physics of the singularity? I'll take a couple of minutes to talk about the physics of the physics of singularity. Okay. اوكي فهمنا شو نقصد بالفيزيكس اوف سنجولاريتي؟ شو؟ مش واضحة؟ We don't know anything. Okay? Yes, there are many theorists out there that each with his or her 10 different competing theories of what a singularity is and the physics of singularities. But when you should always keep in mind, when not for any issue, not only singularities, when you have more theories than the number of theorists out there, then you don't know anything about that issue. Okay? And things become points of view. All right? ماشي? Now, why don't we know anything about singularity? Simply because we don't have a successful quantum theory of gravity. Okay? That's the big issue here. If we have a successful quantum theory of gravity, then we should be able to know the physics of the singularity. Now, if you were able to quantize gravity successfully, please let me know. Okay? Please make sure that you first write it in detail, in complete detail. Let me know about it. Explain it to me in detail. I'll take you on a trip to a very secluded area in Lebanon, and that will be that. Okay? And I will the Nobel Prize. Fine? So don't tell me. Really, there's a Nobel Prize in quantizing gravity. We have these two very successful theories in physics, quantum mechanics and general relativity. Each in its own domain is completely successful. We're still studying and proving the successes of general relativity till now. Since 100 years till now, we know each and every, with every single refined experiment, that general relativity is correct. We also know that quantum mechanics is correct. You bring them together, يعطيك العافية معلم. Every now and then you'll have an infinity and something here and there. ما حدا عارف شي مشي. All right. Now, let's see how we can make use of black holes. Nature relies on black holes. If it weren't for black holes, we wouldn't be here. Black holes, because there are black holes, the universe is the way we know it. If it were not for black holes, all heavy elements, iron وطلوع, يعطيك العافية مالي. Don't bother. Okay? Usually the birth of black holes is associated with very explosive phenomena. So when a black hole forms, you'll have an explosion. And the explosion will destroy the stars or whatever that came before the black hole, scattering its ashes all over the place. Ashes, يعني, I'm using it in the poetical sense. All the different elements. And with successive in stellar evolution, I think there will be talks on stellar evolution. Stars, as they evolve, they create new elements. The elements in the periodic table are created in stars. Helium fuses to hydrogen, hydrogen fuses to helium, helium to carbon, so on and so forth, until you reach the heavier elements. There you need explosive mechanisms to create these. Now, usually these explosions, supernova explosions and whatnot, end in the formation of black holes. So the black hole forms and the star explodes. عصف الانفجار, sorry, we're becoming familiar with these terms too many times, will scatter the newly created elements, iron, uranium, and all the rest. Then this material will be collected by, will contaminate the gas in the area. That gas will form new generations of stars, and maybe those new generations will form new planets, and those planets will have intelligent life, and you know the rest of the story. Okay, so nature uses black holes. So black holes are real, and the very argument for the reality of black holes is that we exist. شو بعد بدك أقوى من هيك؟ Fine. Okay. Now, the formation of black holes is very energetic, and black holes are the highest efficiency engines in the universe, and I will explain. In free fall, in the gravitational field, gravitational potential energy is converted to kinetic energy. The more you fall, the more kinetic energy you gain. Now, remember, the black hole is the most compact mass arrangement. It allows you to fall all the way from infinity to very close to the center. Take, for example, Earth. If you were to fall from infinity to Earth's surface, you will hit the ground at a speed of 11 kilometers per hour. It's the same as the escape, by the way. Okay? Now, Earth's surface has a radius of 6,400 kilometers. 6,400 kilometers. If Earth were turned into a black hole, you will be able to fall a much larger distance, and consequently your end speed before you plunge into the black hole, before you cross the event horizon, will be much higher than 11 kilometers per second. And consequently, the kinetic energy that you will gain is much higher. How much? I'm not going to go into the detail of these things, but it's almost 10% of the rest energy, mc squared. 10% of the rest energy. Fusion, which being sold as the ultimate clean energy source, has an efficiency of 0.7% of the rest energy of the 4 hydrogen nuclei that you put in. Okay. Fusion has an efficiency of 0.7%, whereas falling into a black hole will release almost 10% of the rest energy of the mass that's falling in. That's a huge efficiency. That's a huge efficiency. That's the maximum that you can get. That's very simple. It's just converting gravitational potential energy into kinetic energy. It's your first course in classical mechanics. Okay. So let me discuss now real black holes. There are stellar mass black holes, and they are the result of the evolution or the end product of the evolution of high mass stars. Their masses are usually 10 solar masses, tens of solar masses, and we have a pretty nice picture of how stellar mass black holes form. You start with a huge star and starts converting the elements, creating the elements until you reach iron. Iron is a huge nucleus. It contains, each iron nucleus contains 26 protons. So the Coulomb repulsion between those protons is huge. Not even the intense gravities in the cores of huge stars is able to overcome the Coulomb barrier there. So when a star is collapsing, it will keep on collapsing and collapsing, and things will fall into a black hole. Now, this is an oversimplification. The outer layers of the star will be shut out, and you will have the supernova explode. But stellar mass black holes are relatively, we have a decent picture of how they fall. Now, what we don't know is how supermassive black holes fall. Supermassive black holes are present in the cores of almost all galaxies out there in the universe. And here, when I say supermassive, their masses are 1,000,000 to billion. Okay? A huge masses. We don't know how these supermassive black holes form. Did the galaxy form first and then you form the black hole? Or did the black hole form first and then you form the galaxy? So here you have the egg and the chicken problem. Okay? Fine. So for the rest of my talk, I'm going to talk, for part of my talk, I'm going to talk about active galaxies. Now, what are active galaxies? Active galaxies are galaxies that are powered by gravitational inflow of matter into the black hole. So as I said, every galaxy has a black hole at its core. Now, if there are gases inside that, in the nuclear region of that galaxy, then that gas will accrete, will fall into the black hole and produce non-stellar phenomena. Okay? Now, active galaxies were discovered in 1940s. Astronomers were looking at galaxies, and some of them, they had very strong cores. They had strong cores that are very bright, brighter even than the whole galaxy. And moreover, when you put in a spectrum and want to form a spectrum of the center of the galaxy, then you will have a spectrum that does not look like that of stars, with emission lines and crazy, all of that. Okay? Now, just take a small intro to galaxies. Galaxies come in all shapes and sizes. You have spiral galaxies like our own, and some of them, many of them, have black holes at the centers. Some of those black holes, as I said, have gases close to the nuclear part, to their cores, and then the black hole will become active. The gas will start falling into the black hole. As it falls, it rubs. Those gases will rub on each other and produce the non-stellar spectra. In other cases, it's just quiescent. There's a black hole there. It affects the orbits of the stars, and that's that. Another kind of galaxies are elliptical galaxies. Basically, they look like deformed footballs. Okay, they are ellipsoids. And there's something in between, an ellipsoid living inside a huge disk. هذا اسمه lenticulars. شكله جاي لونتين من العدسة يعني. Lentils. Okay. And there are the irregulars. They are basically galaxies in formation or the leftovers. So, for example, the small Magellanic Cloud and the large Magellanic Cloud, they are two satellite galaxies of the Milky Way. You can see them from the southern hemisphere. They are irregular galaxies, and they are the leftovers from the formation process of the Milky Way. Now, observations of AGN, they have rapid variability from a very small small volume. Remember, the size of this active region that I'm talking about, that bright thing, the thing that's brightest than all of the stars in the galaxy, is roughly the size of the solar system. So you need a very compact energy source, and the only energy source that can give you that amount of energy from that small region is a black hole. There's no way. ما في شيء غيره. No, not fusion, not stars, nothing. It's a gravitational potential energy release. So as I said, that is just supermassive black holes. Just to recap, millions to billions the mass of the sun. They reside at the centers of almost all galaxies. It starts to accrete. I don't want to go into it. The nuclear fusion is 0.7%. I don't want to go into these things. First radius, هذا شفناه هون قبل. AGN Physics. Those of you who are into this thing, these slides will. I think my talk is being recorded, and I can make my slides available for you if you wish. You can go through these equations, but basically these equations are, I told the story of these equations in plain English. Okay, fine. So just quickly, M87, because I'm going to talk about it. M87 is an elliptical galaxy. It's shown here in the inset. It's a huge galaxy, and we know that it contains a supermassive black hole, and an active supermassive black hole at that, because it shoots a jet from its center that extends all the way to the outer regions of this huge galaxy. So what does this thing look like? You have the black hole here, gases here, and the accretion disk, and then a torus around it. Now, they come from in all different shapes and sizes of the active galaxies. Sometimes you will hear that they are Seyfert galaxies, broad line region, narrow line region. They are the same type. There's only one kind. It's depending how you look at it. If you are looking at it through the jet, it's called a blazar. If you are looking at it in the plane of the disk, you'll see a Seyfert 1. If you are looking at it from this side, like من هذه الquadrants من هون, you'll see, sorry, if you are looking at it from the plane, هذا اللي هون, from the plane of the disk, you'll see a Seyfert 2. You'll only see certain features of it. If you are looking at it from these sides, like oblique, you'll see type 1 and what is called type 1. Okay, many different shapes and sizes, but they are basically the same anatomy. Now, in the early days of the Hubble Space Telescope, late 90s, astronomers started taking pictures of galaxies, and that's what I mean. Shafin, do you see this here? That's an elliptical galaxy here, and that's its core. That is its core. If you take a picture of this galaxy with just a ground-based telescope, you'll see a huge galaxy with a very bright star. That's not a star. That's the core of the galaxy. If you zoom in using the Hubble Space Telescope, you'll find this torus here that's hiding inside an accretion disk. And if you look for other features, you'll see indeed it's an active galaxy or some kind of a galaxy that harbors a black hole. So you'll see that's the torus. Okay, مثل donut يعني. Torus is a donut. That's the donut. That's another picture of that, of similar things. And here you see this is in the radio and optical. So this is, you see the jets that are coming out of the galaxy, radio jets. And in the center, very inner regions, you'll see this torus, and then this bright spot that tells that there's a black hole in there. And these are different shapes and sizes. Now, again, how do these form? How do black holes form? Really, we don't know. I'm going to go fast here because I think I'm running out of time. So whether you form a black hole and then a galaxy or the other way around, it's still a matter of debate. But what we know is that the size of the black hole has nothing to do with the size of the whole galaxy. The whole galaxy is not just what you see, but also dark matter. What we know is that they are not correlated. So here I have masses of the black holes and some measure of the size of, or how massive the galactic system is, and they are not correlated. So there's no correlation there. Where we have a correlation is the mass of the black hole and the mass of the bulge. This, bulge. What is the bulge? What do I mean by the bulge? The bulge is this. That's the bulge. Where I have my cursor. That's called the bulge. And it's basically stars. So it turns out that the formation of the black hole and the stars, or how much stars you form, is connected. Think about it. If you are forming, if you have a very powerful black hole at the center, it's going to shoot out jets. Those jets are going to plow through the gas. Okay, inducing star formation, but at the same time, it's going to make the galaxy lose a lot of the gas, and that will throttle star formation. Okay, so it works two ways. It induces and throttles. So that's the control valve there, and that's why the black hole mass runs nicely with the size of the bulge. They are tightly correlated. Those are technicalities. Now what I want to talk, I still have few minutes. I want to talk about okay, can we say a black hole? The answer is yes. First, let me talk about our galaxy. Our galaxy harbors a supermassive black hole whose mass is around 3 million solar masses. And how do we know? It's not an active black hole. Actually, if it were an active black hole, then maybe it wouldn't exist, because it will be shooting out X-rays and gamma rays and whatnot. And maybe that will sterilize the galactic environment and not lead and not allow the formation of planetary systems. I don't know. So it will be, either way, whatever the situation is, we'll be living in a completely different galaxy if our black hole were active. It's not active. So what do we see? Towards the galactic center, there's a lot of gas and dust. So no way you can see it in the optical. Okay? انت وطالع على الجبل شو بتعمل؟ او هودي اللمبات اللي بيحطوهم على البنية حمر. Right? Because red is absorbed the least. Okay, so you can see longer wavelength over larger distances. Go around it. And if you work out the Keplerian motion of these stars, you'll find that the mass of the supermassive black hole is around 3 million solar masses. Okay, so that's for our galaxy. The other galaxy is M87, the one that I talked about earlier. This one. We know that this galaxy is active. And we know that it has a huge black hole, actually millions of solar masses. So astronomers came together and said, okay, let's try to see black holes. And that's what they did. Okay, with the Event Horizon Telescope. Now, why do you want a huge and Earth-sized array of radio and millimeter telescopes? Basically, to be able to see, to resolve the event horizon. As something gets more distant from you, its angular size, its size becomes smaller and smaller. Okay? Sometimes it drops below the limit, the resolution limit of your optical telescope, and then you'll have to forget about it. Okay? Fine. So what do? You have to make your telescope bigger and bigger because to collect more and more signal. Okay? And also you want to use wavelengths that can penetrate through the dust. Now it turns out the easiest way تشتغل بالحديد. It's easy to fashion big telescopes made out of metal than to fashion telescopes made out of glass, huge ones. Radio telescopes مثل الدش تبع الساتلايت are metallic. في الاريسيبو telescope وغيره. So what astronomers did is they connected a whole bunch of radio telescopes all over the earth and combined the signal. Remember, radio waves are on the order of centimeters, tens of centimeters to meters. So when you are combining the signals, you don't need to know the location of the telescopes to within a nanometer. Whereas if you are doing interferometry, if you are doing optical interferometry, then you will have optical interferometry. You're using light. Light has a wavelength of several hundred nanometers. So in optical interferometry, it's being done at the VLT in Chile. It's very difficult, but you have to know the locations of your telescopes to nanometer scales or hundreds of nanometers. With radio, you're fine. Centimeters, 10 centimeters is fine, even up to a meter. So it's easier to do interferometry in the radio, and that's what astronomers did. So they created a big telescope by connecting a big radio telescope by connecting an array of radio telescopes all over the earth. And what the aim was, and was achieved, they wanted to see a shadow of the black hole in Sagittarius A star, the black hole in our galaxy, and the black hole in M87. They achieved that feat in April of last year. We saw the shadow. This is a real picture. This is the event horizon. Gas is glowing around the area, around the whole thing. And this is the shadow. It's just dark. And you have enhancement here and there, and it has to do with the way general relativity bends all the light that's coming from behind and on the sides. But this is literally the event horizon. And only recently, just a few weeks ago, with more and more data analysis and collecting more signal and then grouping signals into epochs, time epochs, they were able to see that this whole thing, this image is evolving. The gas around the black hole is evolving, is moving around, and astronomers were able to see it in real time. Okay, so yes, we can see a black hole now. We can see the shadow of a black hole. How? See it in contrast in front of a bright background. So you see the shadow. Okay, so was general relativity correct? Yes, because the form of the light here is exactly as predicted by general relativity. The size of the shadow is also matches the Schwarzschild radius for a mass with the given mass of M87. Okay, so it's a success story. The other was the detection of gravitational waves. When two black holes collide, they sent ripples in space-time itself, and that was done in the study was in 2016. Okay, and astronomers. So what do we mean by ripples in space-time? Think of space-time as an elastic. So if you want to just be able to see it, think of space-time as a rubber sheet. Okay, it can stretch and contract. When a wave passes, when a gravitational wave passes through that sheet, it can take us. So this is a static background. So it can, when a wave passes, it can either stretch it in this direction, call it the vertical, or stretch it in the horizontal direction. Okay? So what they did is they have a LIGO, which is a gravitational wave observatory. And that's, if you think about it, it's opening a whole new window to the universe. Okay? Ever since we can remember, humanity can remember, astronomy is based on using light, right? Or the electromagnetic spectrum, radio waves to gamma rays. Now with gravitational wave astronomy, we have opened a new window to the universe, and we're able to detect the masses, to measure the masses of black holes, their radii, and everything. It's basically, it's just like plucking or hitting the surface of a tambourine, tabl. These are the oscillations, the vibrations of it, and it agrees exactly with what Einstein predicted and general relativity predicted a century ago. Okay? So you can only see the signal if two black holes merged. If it's something other than black holes, then you will not see the signal. Okay? Fine. I think that's enough. I'll stop here, and we'll be happy to answer your questions.
Okay, now we'll be receiving some questions. We'll start with Mahmoud Kalash. تفضل.
Hey, Doctor, thank you for the nice presentation.
Hello, sir.
I would like to ask about the physics of singularity, and not about the physics of singularity, actually, about the reason why we can't study the physics of singularity. I have two arguments. Is it because we can't reach this singularity point experimentally, or can't provide the experimental environment to study this singularity point, or is it because the theories till now reach at some point a paradox with or a wrong logic or something like that when they process with their theories, or is it both together?
It's more of the second, more of the theoretical, because when do you know that you are in trouble? When your theories give you infinities. So for example, how did people know that, okay, maybe classical physics is not completely correct and we need to upgrade physics 2.0, modern physics, with Max Planck, right? And the black body curve at shorter and shorter wavelength. If you continue the Rayleigh-Jeans law, it will go up to infinity, right? Why does it go up to infinity? Because your theory is wrong.
Okay. So it's more about...
So we needed quantum mechanics. Basically, what was the first step in quantization? That's saying that the radiation field comes in packets. E is equal to h nu frequency, h times frequency. And that is and then made going up, right? It made it go down smoothly back to zero.
Okay.
Okay.
Second and last question, can you go back to the LIGO interferometer that you showed about gravitational wave? No, when you showed some static background. Yeah. What do you mean by this static background and stretch?
Okay. There's no gravitational wave.
Yeah, this static background, what is it actually?
Meshi, just space-time with no gravitational wave, nothing. So it's your stretched rubber sheet with no disturbances.
Yeah, but
Okay.
in terms of experiment, I mean.
ما هذه experiment. Think of it as no gravitational wave passing through. When a gravitational wave passes, it's going to make this circle. هذه فيك ترسمها أنت. هذه if you bring in a rubber sheet, stretch it, hold it steady, and draw a circle on it. Okay? Ink on rubber. Ink cannot escape, cannot move. Now, when a gravitational wave comes in, the gravitational wave affects the fabric of space-time.
Okay, and then this generate ripples.
This generate ripples.
And it
how
will
can you
affect...
visualize them
Yes.
in two perpendicular directions? They're stretching in this direction and stretching in this direction.
I mean, there should be something to sense, like to find some resonance or some vibrations.
This is a simplification, just to show. Actually, both happen at the same time. هذه decomposition.
Okay,
along the x-axis or along the y-axis, if you want. Okay.
Okay. Thank you.
Okay.
هي أسئلة بالشات دكتور.
اوكي يلا تعال شوفوا. الآن بين ما عندي قبل شوي إنه في 4 إيه هون 9 صار. اوكي هات نبلش. Can raise their hands. اوكي في question من محمد نعمة. At the formation of a black hole, why isn't all the ashes elements created after the explosion sucked back into the black hole? Basically, anything that's created beyond the event horizon can escape. Okay? Anything that's created beyond the event horizon can escape. So those elements are created beyond the event horizon, so they can escape. And if there is an explosion, so they can escape to large distances. All right. Now the other, في من مير عقل. I wanted to ask, why does an active black hole shoot jets? Okay. It's a simple question, but the answer could be very complicated. It's when this gas is falling into the black hole, it's going to start bumping into each other. Okay. And the bumping is so hard that sometimes, and because of the rotation and the angular momentum that's involved and everything else, some stuff will just will become shot as jets. And if you notice, the jets are shot along the rotational axis of the system. Okay, it's because of the hydrodynamics of the problem.
دكتور عندي سؤال لو سمحت.
ايه تفضل.
من بعد سنة الماضي أول صورة للبلاك هول طلعت، نحن طلعنا بشي ثيوريز جداد ولا بس إنه عملنا بروف لجنرال ريلاتيفيتي أو يعني نحن عملنا ستيب فورورد؟
لا no, we were able to finally see a black hole. إيه؟ يعني أوقات theories جديد ما عملنا شيء. بعدنا أينشتاين وكوانتم ميكانكس. Both are a century old almost. But now, with this one, then you can make more detailed measurements. And whenever you have more detailed measurements, you can get a clearer picture of what is going on and maybe shed light on how these supermassive black holes come into being.
Okay, thank you, Doctor.
Welcome. اوكي تشوف كم باخذ لي كم سؤال ولا بوقف؟ مين البوس؟
ايه دكتور.
قالوا لي بعمل.
You can continue. فيك تاخذ كذا سؤال.
بس لنحكي للي يحضر. هلا صار فيكم ترفعوا ايديكم وبتسالوا شفهي. اوكي
مزبوط.
Okay, from Furad Jabri, given that the universe may have started from a singularity in a Big Bang and that it seems that an awful lot of the universe is going to end up at the singularity inside the black hole. Is it possible there is a connection between the two? The shortest answer is we don't know. Now, what's so peculiar about singularities is that singularities are a natural state of existence of matter, a natural configuration. Okay, weird as it is, singularities are very natural. We don't understand them. That's tough luck for us, but they exist in nature. Okay, so what is the connection? It's just the physics that's connecting them. It's not that this singularity will be physically connected with that singularity. And the reason, again, why do we say that there's a singularity at the beginning of the universe? Simply because our theory is if we run everything backwards, the video of the universe backwards, we'll get R is equal to 0, density equal to infinity, and temperature equal to infinity. Whenever we have infinities, that points to our ignorance, and that's the singularity. Okay, so maybe when we have a viable, a correct theory of quantum gravity, maybe we'll find that those singularities are not actually singularities. They are something else. They have structure to them. I don't know. For example, physicists thought that protons were, in the early days of particle physics, that protons are point particles, and then we found elementary particles, and then we found that they are made out of quarks, 3 quarks. So we don't know. Okay, another question. Can we say that there is a relation between... No, هذه جاوبتها عنها, so we don't know. Entanglement, المدري شو, ساعتها anything goes إذا بدنا نفوت هيك. Okay, Peter Matarha, I just want to ask if we can't see someone entering a black hole because the black hole absorbs all the light or because of time dilation. No, we'll see them just at the singularity. We don't see them after they cross. So that's why I gave that joke of your image will be frozen for all eternity at the event horizon. That's the last thing we'll see of you. Just at the event horizon. Okay, برجع. Is it من فراغ جبري again? Is it possible for the singularity of a sufficiently massive black hole to distort space-time to the extent where it ruptures the singularity, exploding into the void beyond giving rise to another Big Bang? In the absence of a theory that describes what a singularity is, I don't know. I can't even begin to speculate. Maybe it gets so massive that it will create dragons. I don't know. Right? We don't know what happens. Right? Other questions?
Okay, David.
دكتور دكتور عندي سؤال. ليه الإيمج فروزن؟ لأنه التايم بيوقف أو مرة سبب ثاني؟
It's لأنه التايم بيوقف. And it takes it's actually more than that, because as the photons are climbing out of the potential well, مش بس بيوقف, and you look redder كمان.
نعم أطرش سوري.
You look redder. باين وجهك أحمر كمان. So if you're screaming, you'll be a red cover.
ماشي دكتور.
Okay, Halim.
Hi doctor, it's Halim.
حليم, لك كيفك؟
ماشي الحال.
شو أخبارك؟
والله
مشتاق لك.
the confinement. It's always a pleasure listening to you, doctor. Even
Thank
after
you.
4 years. Actually, I don't have a question. I just had a comment. I'm just glad that you mentioned gravitational waves. I mean, it's the ultimate proof of the existence of black holes.
Exactly.
And, do much more things with it, like the recent proof of the existence of intermediate black holes. I mean, you heard about it. Do you have anything to comment about this new discovery about?
No, I'm unfortunately I'm not working on these things, but the problem in astrophysics is we don't know how these intermediate black holes form.
Yeah.
Or they seem to be too massive. يعني how did 70 solar masses or whatnot, too massive for stars. And apart from that, I don't know what astrophysical mechanism can form them.
I see.
So أنت عم تشتغل على gravitational waves.
Yeah, actually
multi what? Sorry, عطشت.
very high energy.
عم بتقطش، ما عم بسمعك منيح. هيك رح وقف الفيديو تبعي بركي.
Yes, your slides also, please.
I will stop sharing. Okay. ايه سوري حليم، شو كنت عم بتقول؟
كنت عم بقول لك عم بشتغل بإطار مالتي ماسنجر استروفيزكس.
اوكي.
يعني
سو نيوترينوز كمان؟
ايه فولو اب. actually عم
Okay.
بشتغل within very high energy observatories مثل HESS collaboration, and we do follow up of all the messengers that come gamma ray,
Great.
GRB.
Interesting. Good. انبسطت انك جيت. dropped in من فرنسا.
Yeah.
Good. Thank you for coming.
اوكي
سؤال.
بعد في أسئلة؟
السؤال إذا في مجال.
ايه تفضل.
ايه تفضل. انا اذا الاورجنايزر ما عنده المشكله انا ما عندي مشكله.
How can we imagine the 4 dimensions made by Einstein? How can we يعني ممكن الرابع dimension اللي هو الزمن فينا نقول بيمشي بخط واحد مستقيم؟ وهل هذا له شو اسمه philosophical بياخذنا على اشياء philosophical انه مثلا deterministic يعني الكون كله deterministic؟
Like speculations I don't get. I prefer not to get into it because there's no end to it. There's no bottom. What we know is that the world is the way it is according to relativity. And when you go and do experiments, you'll find that the relativity is correct. Sometimes it doesn't make sense to us because sometimes it turns out that our logic is too limited. يعني case in point, the previous speaker Noor was talking about Galileo and the others. When first time Galileo showed his telescope, some people refused to look through the telescope. انه the universe is the way it is وخلص ما بقى تفرجيني اشياء ثانيه ما بدي وجع راسي. Sometimes humans are very limited. يعني if you think about it, quantum mechanics does not make sense at all as a human sense. As a human sense does not make sense at all, but it's correct. And it has أكثر من هيك, its most nonsensical aspects are driving a revolution now. Quantum information sciences.
100% هذا بيعزز اللي كنت عم اقوله انه اذا بدنا نثبت يعني العقل ما له دور.
لا ما هيدا كيف عم بوصل لهم انا بغير العقل. بس اللي
عم
عم بيصير لا عم بيصير مش العقل مش عقل الانسان عم بيصير الانتربريتيشن تبع الانسان بيكون محدود اوقات. interpretation تبع الانسان عم بيكون محدود. بدنا نوسع فكرة لانه بس ارسطوطيليان لوجيك مثلا. For example في شيء اسمه topos logic. Aristotelian logic is built on the premise that you know that the person who's passing judgment has complete knowledge of the system, past, present, and future. مطلق. In topos logic, it allows for ambiguity. إنه I only know part of the system. So نحن بالعكس العقل البشري بيتحمل قد ما بتفتح له. بس اذا بدي اجي اقول انا لا ما بدي اطلع بالتلسكوب لان رح اشوف نجوم جداد يمكن ما كنت شايفهم قبل، او رح اشوف الفيزز اوف فينوس، او رح اشوف مدري شو، او رح اشوف انه هودي البلانيتس نجوم السياره، البلانيتس مينز ذا واندرر، انه رح اشوفه انه هيدا لا اتس ديسك سو اتس بلانيت لايك ايرث وهيك، وبدي تخربط لي طريقه تفكيري. هيدي خلص المشكله بهيداك التفكير مش بالعقل البشري ككل يعني.
هي عادة الماثماتيكال مودلز ميك سنس أكثر، يعني العقل مش رح يتصور الكونتنت.
ما ليش عم بقول لك؟ لأن العقل أوقات how do you interpret them? You interpret them through your philosophical conceptions. أينشتاين، حدا بقول لك أينشتاين بعنا هلا عم نقول إنه أينشتاين صح وما صح؟ general relativity إيه؟ كوانتم ميكانكس ما كان يطيقها لأنه فيها شيء غلط، مزبوط؟ entanglement ومدري شو. هلا we know that entanglement is correct. In quantum information sciences they are finding new and new applications of entanglement. So طيب شو إنه طب ما عواد أينشتاين. Einstein had problems with that the universe is evolving. His philosophical conceptions was, or preconceptions or misconceptions, was that the universe is static. لا بيكبر ولا بيصغر ولا بيتطور، خلص as it is. إجا هابل أخده قال له تعال يا أخي طلب هذا this is my data and it's showing that the universe is expanding. كان حاطط هذه الكوزمولوجيكال كونستنت لأن general relativity allows for an evolving universe. But he added a term cosmological constant by hand just to keep the universe from expanding. Now we know that the universe is not only expanding but its expansion rate is accelerating. So in some sense أينشتاين حتى وقت اللي بيغلط بيكون غلط وصح لهالدرجة يعني. بينما نحن وقت اللي بنغلط خلص go home.
لا لانه في ماثماتيكال موديل مش من عقله.
ما هيدي لان بيس واعترف بغلطه and called it the biggest blunder in his life. And when he was shown that evidence that the universe is expanding, he said, okay, sorry, I was wrong. My philosophical or cultural preconceptions took the better of me and I did a mistake. بالماث فيك كمان ماث لحاله ما هو ما اشتغل ماث غلط، ما غلبط بالماث ماشي. you can put a constant term in that equations if you know where to put it correctly and nothing will change. You won't make any mathematical بس وين القصة من الفيزيكس. Now the other problem هلا اللي عندنا اياه انه we don't know where that cosmological constant is coming from to lead to the accelerated expansion of the universe, and that's another Nobel Prize.
هو انا هذا اللي حيرني من قبل، انه على وقت الجيوسنتريك موديل ما كان في دليل انه يمكن ما في ماثماتيكال موديل.
لا ليك اذا بتاخذ geocentric model if you stick to naked eye observations مش الانسترومنتس تبع تيكو براخي, the only logical conclusion that you can make is that the Earth is at the center. The Greeks were not idiots. They were making the best of the data that they had at hand. They were not idiots. انت هلا اليوم بنفس عمول بنفس شروطهم رح توصل لنفس الكونكلوجن, بس وين بلشت الداوت؟ actually في واحد كمان بالايام الاغريق he said he presented انه what if the sun is what if the earth, but his evidence was weak.
بس
so his theory was not adopted simply because the geocentric model as a practical model was very powerful up to, you know, naked eye observations. When you start using instruments, very refined instruments that like the ones used by Tycho Brahe, then عيوب الجيوسنتريك موديل بتبين.
100%. بس بالحضاره العربيه بنلاحظ انه مثلا في علماء ما كانوا مقتنعين بهذا الجيوسنتريك موديل.
ليك الحضاره العربيه فاتوا, ما تنسى الحضاره العربيه ما اجت من فراغ. الحضارة العربية الوريثة الطبيعية لكل العلوم اللي اجت قبل.
بالضبط، هو اللي عمل
اخذوا اللي عندهم، ايه اخذوا الموجود وطوروا قد ما فيهم.
رغم انه ما كان في تلسكوبات، بس
لا
بيأمنوا
ما
انه
قبل لك.
الارض بتبرد.
يعني ما كان again يعني تكنولوجيا ما مساعدتهم بعنا لهلا. كان بالديتكشن اوف gravitational waves or detection of the event horizon. طب ما راديو تلسكوبس من الستينات. انه هلا حدا طلع عبقري طلعت براسه انه يطلع فيها، مش مفكرين قبل من الستينات. But technology was not advanced enough to allow them to do what they did now. Like حتى لو أخذ data, you did not have the computational power to process it.
Exactly.
Yeah.
Thank you.
Welcome.
Any other questions? Okay, then we can end. Mariam?
Yeah. Thank you so much, Dr. Bassem Sabra, for your wonderful
Thank you for inviting me.
really fun talk. It was really fun, and you showed us the mysterious part of the black hole, of our beloved black holes. Thank you so much. It was an honor to have you. Okay, now does anyone have any other question other than for Noor, for example, or something like that?
يس، كان بدي أسأل شيء لنور بخصوص الهيستوري اللي حكيت عنها.
اوكي بس خلينا نشوف نور وين.
ايه انا هون عم بسمع.
اوكي تفضلي.
انا نور بتعرف انه خلفيتي مش فيزيائيه، بس اهتمامي بالموضوع خلاني اسال هذا السؤال. انه نحن وصغار كنا نشوف بالكتب انه الكواكب مصفوفين هيك حد بعض كأن خط مستقيم. بعدين لما كبرنا شوي صار يورجونا اياهم انه هن مثل بيمشوا بدوائر وهميه وهيك. فخطر ببالي السؤال انه هن بيمشوا بنفس السرعه او كيف يعني مسارهم مضبوط، وكمان ليه بتختلف سرعه كوكب عن الثاني، انه شو الفرق، ليش ما بيمشوا مع بعض، هيك شيء يعني.
ماشي، هلا اول شيء تبع اول سؤال، عادة الصورة اللي حاطينها هي بس حتى يفرجون انه هن ترتيبهم كيف، اي اقرب وحدة واي ابعد وحدة. اما مسارهم فهو اللي حكى عنهم كابلر، انه ليش بيمشوا بسرعات مختلفة. طبعا لهيدي اللو انه الاير اللي بدها تقطعها بتايم معين بدها تكون متساوية، يعني كانت بأول الإليبس ولا بوسطه ولا بآخره. فلهيك لما بدها تقرب على الشمس بدها تزيد سرعتها حتى تقطع مسافة أكبر، ولما بدها تبعد عن الشمس بدها تقل سرعتها حتى تقطع مسافة أصغر. ما بعرف إذا جاوبتك على السؤال.
أوكي.
هذا السؤال بالضبط.
إيه أوكي ماشي وصلت.
أوكي بعد في حدا؟ Okay, مفروض we're finished for today. Thank you all for your attendance. Thank you for being here with us. We hope you enjoyed and it was beneficial for you. We hope to see you in the upcoming days, every day, of course. Every day there's new topics, new things to discuss. So thank you for your presence. At last, I just want to say you can follow our social media platforms like Instagram and Facebook to keep updated and stay in the loop. And you can ask us any questions through email and we can answer you as soon as possible. Other than that, thank you for your presence again. That's all. See you soon. See you tomorrow. We hope that.